This title of my lecture, The Sun, Our Star, was chosen by the organizers and not by me. So this title might have conveyed the impression that this lecture is going to be a very comprehensive introduction to all aspects of the sun. But as I started preparing the lecture, I realized that solar physics, the study of the sun, has become such a vast subject that it is completely impossible for anybody to give a comprehensive introduction to this subject in half an hour. So I shall mostly focus on one aspect of the subject, solar activity. In a few minutes, I am going to explain what that is, and you will see that solar activity has very intimate connection with space science. But at the outset, I should also point out that there are many other important topics in solar physics which I would not be able to cover in this talk. So, for example, some of you may know that Ray Davis won a Nobel Prize in physics for the discovery of neutrinos from the sun. So certainly I shall not have time to discuss solar neutrinos and some other important topics. So let us come to solar activity. So what is it? So according to elementary textbooks of astrophysics, a star is a spherically symmetric hot ball of gas inside which nuclear reactions are taking place. Now, there are many phenomena in the sun which makes it much more complicated and intriguing than a simple spherically symmetric hot ball of gas. So such phenomena are collectively called solar activity. So let me begin by recounting some examples of solar activity. So the type of solar activity which has been studied for the longest time happen to be the sunspots. So these are dark regions on the solar surface, and some of the largest sunspots can be larger than the Earth. So here I show a photograph in which you see two large sunspots side by side, and the size of the Earth is indicated here for comparison. And in a few minutes, I shall discuss why it is you very frequently see two large sunspots side by side, or why sunspots appear in pairs. So in 1844, Schwabe discovered that sunspots have a 11-year cycle. So here I show a plot of sunspot number against time for the last 400 years or so. So you can clearly see this 11-year periodicity, but you also see that this is not a very regular cycle. It has lots of irregularities. So the next manifestation of solar activity I want to mention is the solar corona. This temperature of the surface of the sun is a little less than 6,000 degrees Kelvin, but some regions of the corona can be as hot as 2 million degrees. And if you look at this image of the corona taken during a total solar eclipse, you can see that it is far from being spherically symmetric. Now, according to simple stellar structure models, the temperature and density of the sun near the solar surface would go to zero, and beyond the surface, there would be nothing more. So why is the solar corona there, and what causes its very high temperature? So lastly, another important manifestation of solar activity is the solar flares. These are explosions which typically occur above sunspots. So here I show a video of a solar flare. So the energy released in a major flare can be of the order of 10 to the power 26 joules. So for comparison, remember that the atom bomb which destroyed Hiroshima had an energy of 10 to the power 14 joules. And these are unbelievably energetic events which even affect our lives, even though we are so far away. So on March 13, 1989, about 6 million people in Quebec, Eastern Canada, were without electricity for 8 hours. And apparently this power blackout was caused by large flare which was seen by solar astronomers 3 days earlier. So these effects of the solar disturbances are maximal near a geomagnetic pole. And since one geomagnetic pole is very close to eastern Canada, that is one particularly vulnerable region. So when solar astronomers first started studying solar activity, it was initially thought that that different manifestations of solar activity are completely unrelated phenomena. Maybe the people thought that astronomers thought that solar corona has nothing to do with sunspots. So it was mainly during the second half of the 20th century when solar astronomers realized that there is a sort of underlying unity behind all these different kinds of solar activity. Basically, all these types of solar activity are caused by one entity, the magnetic field of the sun. So the study of solar magnetic field began in the year 1908 when Hell found evidence for Zeeman splitting in the spectrum of a large sunspot, and from which he concluded that sunspots are regions of strong magnetic field of about 0.3 Tesla, which is approximately 5,000 times the magnetic field near the geomagnetic pole. And within the next few decades, astronomers realized that magnetic fields are ubiquitous in the astronomical universe. So most stars, planets, and galaxies have magnetic fields. And Hale et al. Also made another very important discovery a few years later. I already pointed out that often we see two large sunspots side by side. So Hale et al. Found that in such sunspot pairs, the two sunspots usually have opposite polarities. If one of them has positive magnetic polarity, the other has negative polarity. So the most plausible explanation for that is that there must be some strand of magnetic field underneath the sun's surface, which is poking its nose to the surface in this kind of fashion. So if these two intersections with the solar surface become the two sunspots, then in one sunspot you have magnetic field lines coming out, making it a positive polarity sunspot. And in the other sunspot, you have magnetic field lines going down, making it a negative polarity sunspot. And if this idea is correct, then the solar corona would be full of such magnetic loops above the sunspot pairs. And we now know that this is the case. So within the last few years, solar astronomers have developed ingenious techniques for mapping these magnetic loops in the corona. And here you can see a beautiful image of magnetic loops in the solar corona. And now I show you something which I find absolutely fascinating, a magnetogram map of the solar disk. A magnetogram measures the magnetic field at every point of the solar surface. If the magnetic field is positive, then white color is put. If it is negative, then black color is put. And if it is too weak, then gray color. So you'll see here that there are many places where you see a white patch and a black patch side by side. So this means that there are two sunspots here. One of them has positive polarity and the other negative polarity. And you also may notice that in the northern hemisphere, you have a white patch or the positive polarity sunspot on the right side and the black patch or the negative polarity sunspot on the left side. And in the southern hemisphere, it is opposite, this with black on the right and white on the left. And things remain like this for one cycle of 11 years. So if you are to produce a magnetogram map 11 years later, then we'll find that in the northern hemisphere, black has come to the right and white has gone to the left. And in the southern hemisphere also a similar reversal. So you actually have to wait for 22 years if you want the magnetic field to come back to its original configuration. And if you look at this distribution of magnetic fields inside sunspot pairs, you can almost get a feeling that there must be a magnetic field structure like this underneath the sun's surface. So this magnetic field components, which we call toroidal magnetic field, which is in opposite directions in the two hemispheres, and if these parts of this toroidal field were to float up to the surface exactly as indicated in this image, then you can easily convince yourself that if parts float up to the surface, then you would get a sort of a distribution of magnetic fields in bipolar sunspot, exactly as you see in this magnetogram map. So now the question is, how can we theoretically understand this kind of magnetic structures and how do they arise? So coming to the theory, I would first say a few words about the plasma state, the fourth state of matter. So Meghnad Shah studied how on increasing the temperature of a gas, its atoms gets broken into positively charged ions and negatively charged electrons, and eventually the gas gets converted into a plasma. So because of the electrical attraction between positive and negative charges, they remain well mixed. So if you consider a small volume of the plasma which has sufficient number of charged particles, we will find that positive charge nearly balances negative charge. So you may wonder, then does the plasma behave like a neutral gas? So no, the difference becomes clear if you put an electric field. So a neutral gas like the air is a bad conductor of electricity, but in a plasma, an electric field makes ions move in the direction of the electric field and electrons move in the opposite direction, giving rise to a large current. And you know that the currents give rise to magnetic fields. So you can have complicated interactions between the plasma and the magnetic field. So how can you study such interaction? So even though air is made up of molecules, you can treat the air as a continuum for many problems of air flow. Similarly, many problems of solar activity can be studied by regarding this plasma as a continuum, and then you can study the interaction between the plasma and the magnetic fields by combining electromagnetism and fluid mechanics. And this combination goes by the tongue-twisting name Magnetohydrodynamics, abbreviated as MHD. So I don't have time to get into a detailed discussion about the basics of MHD, but let me just point out that there is a very important dimensionless number in this field, is magnetic Reynolds number. So here I point out how it is defined, but let us not get into those details. Just note that magnetic Reynolds number is directly proportional to L, where L is the size of the system. So this means that the larger the system, the bigger is the magnetic Reynolds number. So this magnetic Reynolds number turns out to be much smaller than 1 for laboratory plasmas and much larger than 1 for astrophysical plasmas, and it follows from MHD equations that the plasma behaves very differently in these two limits. And this limit of a large magnetic Reynolds number, Alfvén proved a very famous theorem in 1942, Alfvén's theorem of flux freezing, that magnetic field is frozen in the plasma and moves with it. So what exactly do I mean by that? So let me illustrate by a thought experiment. Suppose you have a block of plasma between the pole pieces of a magnet, and suppose this block is moved sideways, then what happens? So in the case of low magnetic Reynolds number, nothing special happens. The plasma blob is moved here and the magnetic field remains back as it was. But in the case of a high magnetic Reynolds number case, you know that because of Alfvén's theorem of flux freezing, the magnetic field has to remain frozen in the plasma blob. So when the plasma blob is moved here, the magnetic field has to take up this kind of configuration. So some of the most interesting results of MHD are for this case of high magnetic Reynolds number situation, which cannot be tested in a terrestrial laboratory. So one often says that the sun is the best laboratory for high magnetic Reynolds number MHD, and you can MHD to study solar activity, and that subject is called solar MHD. And I would say that there are three very key ideas of solar MHD. So firstly, this magnetic field is frozen in the plasma, which I already discussed. And the other two ideas are not unique to MHD, but even you might have encountered these ideas even in your electromagnetic theory courses, that magnetic field has a pressure B squared over 2 mu, and a magnetic field has a tension along field lines, so that a magnetic field behaves like a stretched rubber band. So now I want to show how, by using these three key ideas, many aspects of sunspots can be explained. Now the sun also rotates around its rotation axis like the Earth in about 27 days. But unlike the Earth, which rotates like a solid body, the sun has what is called a differential rotation, which means that in different regions of the sun, the angular velocity can be quite different. So the angular velocity is largest near the equatorial region. Now think that there is a magnetic field line like this, like a field line of the geomagnetic field. The sun is also known to have such magnetic fields. So because of Alfvén's theorem of flux freezing, the faster moving plasma near the equator would drag this magnetic field line. So after some time, magnetic field line would look like this. And you would see that you now have a strong toroidal field with opposite, which is in opposite directions in the two hemispheres. So if the parts of this toroidal field were to float up to the surface, they would produce bipolar sunspots with oppositely directed polarities in the two hemispheres, as you saw in the magnetogram map. But why should parts of this toroidal field float to the surface? Well, consider a region where there is a sort of a strong magnetic field. Okay, so you consider a region with a strong magnetic field, a magnetic flux tube. So inside it, the magnetic field would have a pressure. And since you expect a pressure balance between inside and outside, you expect that the gas pressure outside should be equal to the gas pressure inside plus magnetic pressure. And that implies that this gas pressure inside should be less than gas pressure outside. And that implies that the density inside may also be less than density outside. And then this flux tube would be buoyant. This is called magnetic buoyancy, which was first pointed out by Parker in 1955. So because of this magnetic buoyancy, this magnetic field, this toroidal magnetic field inside the sun may become buoyant and produce and rise to the solar surface to produce these bipolar sunspots. So largely, why the sunspots are dark? It turns out that heat is transported by convection just below the solar surface. So you see convection taking place surrounding a sunspot, and because of the magnetic tension of the magnetic field inside the sunspot, that opposes the random motions associated with convection, and convection is suppressed to a large extent inside a sunspot. So heat transport is less efficient, and that's why sunspots appear darker. So now you have some idea how, by combining these ideas of flux freezing, magnetic pressure, and magnetic tension, we can explain various aspects of sunspots. Now we come to a very key question. Why does the sun have magnetic fields at all? And what causes the 11-year sunspot cycle, which is presumably a magnetic cycle? And as I pointed out, that most other astronomical objects also have magnetic fields. The branch of MHD in which we try to understand how magnetic fields are generated in astronomical objects So that branch is called dynamo theory. So since I have worked on dynamo theory for many years, I would have been happy to give a systematic introduction to dynamo theory. But I realized that only if I give a 1 hour lecture devoted completely to dynamo theory, then only I can give a sort of an introduction to dynamo theory. So since that is not possible here, I shall just make a few comments about dynamo theory. So in 1955, Parker derived the dynamo equation, the basic equation of this subject, and also gave a model of the 11-year sunspot cycle. So even now, when we try to model, try to understand how magnetic field is generated in in an astronomical object, we start with the basic ideas which Parker gave in this paper. But within a few years, it was realized that Parker's model of the 11-year sunspot cycle, that was not a very complete or satisfactory model, because that was based on the very limited amount of observational data available at that time. So as more and more observational data started coming, it was realized that a more complete and improved model was needed. So from the 1990s, a model started being developed called the flux transport dynamo model. So our group at IIRS has contributed to the development of this flux transport dynamo model. And these organizers told us speakers that we should highlight any work done in India, any important work done in India. And of course, I do not want to make any comment whether our work was important or not. That should be judged by others. But I can just mention that special recognition for our work came about 2 years ago when I became the second Indian to receive the Chandrasekhar Prize of Plasma Physics after Professor P.K. Kao, who received this prize about a decade earlier. So as the citation of this prize says that it was for the key role in developing this flux transport solar dynamo model of the 11-year sunspot cycle. And I should mention that I was lucky to have a succession of extremely brilliant PhD students whom I have listed here. And my work on this flux transport dynamo model was done with them. So the prize might have been given to me alone, but this is a collective this is a recognition of the collective work that all of us did jointly. So anyway, after giving this introduction to sunspots and dynamo theory, let us move to the corona now. So as I already pointed out that that the corona has regions of corona have temperature of the order of millions of degrees, and from a simple application of Wien's law of black body radiation, you can conclude that such high temperature gas would emit in X-rays and extreme ultraviolet, and the upper layers of our atmosphere happen to be opaque to such radiation. So to detect such radiation from the corona, you have to put instruments for detecting X-rays or extreme ultraviolet in space missions and send them above the Earth's atmosphere. And that is routinely done in the last few decades. So here you see images of the solar corona in the extreme ultraviolet taken from space. So on the left side, you see this image of the rotating sun taken during sunspot minimum, and here it taken during sunspot maximum. So you see that the solar corona appears quite different at different phases of the sunspot cycle. And at the sunspot maximum, you see lots of loops. So these are nothing but these magnetic loops above the sunspot pairs. And these are the brightest region, indicating that whatever be the mechanism for producing heat in the corona, that mechanism is maximally operative within this coronal loops. So what could be this mechanism? So magnetic fields in the coronal loops imply that there are also currents, And you know that when a current flows through a metal wire, it gets heated. So could the corona be heated because of the ohmic heating produced by the current? And when order of magnitude estimates were made, it was realized that if currents flow through very large regions of the corona, then too little heat would be produced. So only if we can somehow force the currents to flow through the narrow regions of the corona, then only sufficient heat could be produced. So Parker gave a scenario how that may happen. So you may normally think that the magnetic field in a coronal loop would look like this, but underneath this coronal loop, you have you have vigorous convection, so that will disturb this magnetic field, so that it may have a sort of a tangled appearance. And Parker showed that in such a situation, the current is forced to flow through very narrow regions, and that may produce the large amount of heat in the coronal loop. So after this discussion of the loop, coronal loop, let me come to solar flares. To several scientists develop the models of magnetic, what is called magnetic reconnection, to explain solar flares. So suppose you have a region of plasma on the two sides of which the magnetic field is in opposite direction. If you apply Ampere's law, then you can easily conclude that current density would be quite high in this region. And since ohmic heating goes as J square, so that means that there will be quite a lot of heating produced. So, and you now know that the corona is full of magnetic fields. So suppose some new magnetic flux system emerges from underneath the surface in a region where there is an underlying magnetic field which has a different direction. So at this interface between the old flux system and a new flux system, we would have magnetic fields in different directions on the two sides. So there may be a huge region in where this sort of a magnetic reconnection takes place, causing a large explosion. And when you have these kinds of explosions, often that throws away large chunks of plasma, as you see here. So I shall not open this movie file. So you saw that it throws away large chunks of the plasma. But maybe I shall open, but what happens to them? So they move through the corona in the form of what are called coronal mass ejections, or CMEs. So let me try if I can open it here. Yeah, it's working now. So you can see this coronal mass ejections moving away. So this image is taken with a coronagraph, within which you produce an artificial eclipse by blocking the central region of the by blocking the solar disk with an occulter, so that you can see the corona. And if you look at these CMEs, then you get a feeling that there is some kind of an outward flow from the sun, which is carrying away these CMEs. And what is this outward flow? So you know that the Earth's atmosphere is held to the Earth by the Earth's gravitational field. So you may try to imagine what happens if suddenly the temperature of the Earth's atmosphere becomes much higher, then the Earth's gravitational field will have find it more difficult to hold on to it, and the atmosphere will extend quite a bit against the Earth's gravitational field. So in 1958, Parker realized that the solar corona is so hot that sun's gravitational field would be unable to keep this hot corona confined. So he realized that he suggested that the outer parts of the hot corona would expand in the form of a plasma outflow, which he called solar wind. So at that time, most of the scientists of that era thought that it is quite an absurd idea. But within some 3 or 4 years, solar wind was detected by in situ measurement from space missions, and the density and velocity of the solar wind near the Earth's orbit were found to be in conformity with Parker's prediction. So that is regarded as a sort of a big triumph of theoretical solar physics. And you know that the light takes about 8 minutes to travel from the sun to the earth. Whereas a solar wind takes about 3 to 4 days to cover the sun-earth distance, and these debris of the solar disturbances are carried in the solar wind. That's why after a major solar disturbance, the Earth is affected typically 3 or 4 days later. And the solar wind impinges on the Earth's atmosphere and makes it lopsided like this. And I believe some of the other speakers will discuss the solar wind magnetosphere interaction. So without getting into it, let me advertise a little bit about my popular science book, Nature's Third Cycle, where I have given an introduction to solar physics and also have given a non-technical introduction to the subject of dynamo theory, which I did not have time to discuss at all in this lecture. So if you find this subject interesting, you may want to look at this book since this book was published in Oxford University Press UK, maybe the hard copies of the book are maybe somewhat expensive for Indians, but presumably the Kindle edition is not unaffordable. And so now I come to my last slide with this one particular comment. So a particular academic field has a kind of intellectual appeal if we find that different phenomena studied in that field have a kind of a unifying thread connecting these different phenomena. And that is certainly the case in the study of solar activity. So firstly, to begin with, you have the dynamo process, which produces magnetic fields in the sun. And then due to magnetic buoyancy, the magnetic fields rise to the surface and produces sunspots. And above the sunspots, you have these currents in the loops, which produces the hot corona. And this hot corona drives the solar wind. And one unique feature of this field was that it was one individual, Professor Eugene Newman Parker, who essentially discovered all the crucial links in this chain of causes and effects. So he formulated dynamo theory. He gave the idea of magnetic buoyancy, and he also pointed out how the currents in the loops would cause the hot corona, and he predicted the solar wind. So as Dipankar pointed out, I had the privilege of doing my PhD under his supervision at the University of Chicago. And here is the building laboratory for astrophysics and space research where we all worked. So this corner room was Professor Parker's office, and this corner room here was Professor Subramaniam Chandrasekhar's office, and my office was here next to Professor Parker's office. And since this upper part of this slide nicely summarizes these various ideas which I discovered, phenomena and ideas which I discussed in my talk, so I have not prepared any separate summary slide. So I leave this summary in this form before you and stop here. So thank you for your attention.